So in the last video, we dealt with pressure, mainly hydrostatic pressure. It's how pressure in a certain fluid depends on the depth. That's only with one fluid though. Now I want to deal with multiple fluids, so having one fluid on top of another, such as this situation where I have some oil floating on top of water. In hydrostatic situation, nothing happens here. Stable oil is less dense than water, so it will sit there. Nothing's going to move. What I really want to know is what's going to happen at this interface. So 2, 3, 2 is the bottom of the oil, 3 is the top of the water. How are those two pressures related? As I mentioned, if I'm dealing with just one single fluid, the oil, for example, I can find P2 because it's P1 plus rho. This is rho for the oil, G times that depth. If I'm just dealing with the water, P4 at the bottom of the water is P3 at the top of the water. Density, again, density of water here, G times this H. But if I want to know what the overall pressure at the bottom of this tank is, I need to somehow be able to add these two guys together. And to do that, I need to know how the pressures are related at that interface. And so some of you may have guessed, P2 has to equal P3. So the pressure at the bottom of the oil has to equal the pressure at the top of the water. The reason this is true, again, because nothing's moving. Pressure is related to a force times area. So if I had a different pressure on the top and the bottom, I'd have a different amount of force pushing up and down, and that would cause some motion of this interface. Because it is motionless, the pressures need to be the same, so P2 for the oil has to equal P3 for the water. The reason this is important is because this video is related to the types of pressure gauges, how to actually measure pressure, and the second one we're going to see, manometers use different fluids, so I'm going to have to deal with different fluids and multiple fluids and deal with what pressures are at the interfaces, so I need to know that those will all be constant. Before we get to those more complicated manometers, a simpler form of a pressure gauge is a barometer. You may have heard of these. They usually measure atmospheric pressure. Technically they can measure any pressure change, but usually the way they're set up is you have a tank of fluid, then you have another tube, stick that in there upside down, suck all the air out at the top of the tube so that you create a vacuum, zero absolute pressure. Then on the outside of this tube, I have atmospheric pressure pushing down on it. Up here, there's nothing pushing down on it, so this atmospheric pressure pushes some of the fluid up into this tube. It's going to go up a certain height, delta H. You can then measure that certain height, delta H, and then using hydrostatic pressure equation, P is rho G times H, or in this case, rho G is just gamma, and that measured delta H, you can find the pressure difference. So again, for atmospheric pressure here, I have zero pressure here, so the pressure difference is just atmospheric pressure, and then this height is whatever height of fluid goes up that tube. If I was using mercury, so if this fluid was mercury, this height would be 760, so that's where the units of 760 millimeters mercury comes from for atmospheric pressure. It's directly related to this hydrostatic pressure concept. So manometers use the same basic concepts of barometers, basically hydrostatic pressure. The problem is they're more complicated, generally have more than one fluid or more than one bend, such as the case down here. So I have a pipe, there's some fluid flowing in this pipe. So what I want to do to measure the pressure, I stick this tube with a couple bends in it into this pipe, and I also have a different fluid, so there's some fluid flowing in here, comes down my pipe to a certain level, but then there's this other fluid, so some different black fluid here, and that's going to go up to some level over here, and of course this is open to the atmosphere, so I have atmospheric pressure pushing down there. So based on all that scenario, I want to figure out what the fluid pressure is at that point for. And again, the way this is done is just simple hydrostatic pressure, so a bit more complicated because I have to make it all the way around to point 4. So what I do is I start where I know the pressure. So over here I have atmospheric pressure, so at point 1 I have exactly atmospheric pressure, and then what I'm going to do is basically go my way through this pipe, go from 1 to 2, go from 2 to 3, go to 3 to 4 using hydrostatic pressure relationships, and eventually I'll get the pressure at P4. So next step, I need to know what the pressure is P2 based on P1. So again, hydrostatic pressure, my pressure at point 2 is whatever my pressure is at point 1 plus this height H12 times the specific weight. I'm going to call it gamma B for the black fluid inside my U-tube there. So this guy I can now relate because I know what P1 is. So now I know what P2 is essentially. And now moving along to point 3. There's two ways I can do it, hard way or the easy way. Hard way is I take point 2, I add this amount of pressure, whatever that height is, I then come across here horizontally. When I move horizontally, there's no increase in pressure because there's no change in height. Then I come back up from point 2 to point 3, and at that point, I'm then taking away whatever pressure I added over there. So similarly, I'm basically moving horizontally from point 2 to point 3. So moving horizontally, point 2 to point 3, means that my pressures need to be the same. And then finally, you get to point 4. At point 3, I have some pressure that I know, and then I want to get up to point 4. So similarly, I take the pressure that I have at point 3, and then take away this hydrostatic pressure contribution because I'm going up in the fluid, so I'm going to have less pressure at the top than the bottom. So take away whatever the specific weight of that white fluid is, again, times that same distance, H34. So I put this all together into one equation, essentially take my P4 equal to P3 minus gamma W H34. P3 was P2, P2 was P1 plus gamma B H12, but P1 was P atmospheric. So putting that all kind of all back into the equation for P4, this is the equation I get. So P4, start with P atmospheric, I go down 1, 2, so I add that hydrostatic pressure contribution, then I go up 3, 4, so I take away that hydrostatic pressure contribution. This process leads to what we call the general manometer equation, which is essentially that process. I start at some location P1, I add a bunch of hydrostatic pressure contributions, however times I go down, I add a bunch of hydrostatic pressure contributions, however many times I go up, and eventually I end up with whatever pressure I'm dealing with. Now, I personally don't really like this equation because it's kind of misleading. Notice that my positive one, gamma B H12, the way I did it is when I was going down, and for that to be positive, it has to be one of these guys that says up on it. So these ups and downs are kind of misleading because it's not necessarily what direction you're going, it's whether the pressure is going up or down. So when I go down in this fluid, it's when my pressure goes up, so that's my contributions up. Similarly, but opposite for the down part. Here, my pressure going down was when I went up in my fluid. So generally, I don't really use this equation. The way I do it is the same way I just derived this one. I just start somewhere and then think about getting to the other point, and if I'm going down, that means I'm adding hydrostatic pressure. If I'm going up, it means I'm subtracting it. So example, I have a more complicated scenario. I have air on top of oil, goes through a few bends, back to air, into mercury, and then open to the atmosphere over here. So I want to know what the pressure is at this location, point 2, the air-oil interface, based on all these differences in heights. So the way I'm going to do this is just kind of start where I know the pressure, which is the right-hand side. So here, I'm open to the atmosphere, so I know the pressure right at this point, at that line, is atmospheric pressure. So that's where I'm starting. So I'm right here with atmospheric pressure. Now what I want to do is I want to get to this point down here. So I move through the fluid, move through my mercury. I get to this point here. So I've gone down 80 centimeters in mercury. So my pressure has gone up by whatever the specific weight of mercury is, times 80 centimeters, or 0.8 meters. So at this point down here, I now have this pressure, whatever it is. So now that I'm here, I want to come up through the air to this point right there. So to get to that point there, I go up 100 centimeters. So going up, I'm losing pressure, whatever the gamma of air is, times 1 meter, 100 centimeters. So that now gives me the pressure at this location. I then want to come down through the oil to point 2 essentially, and so I'm going to have to go down 40 centimeters of oil. So that's going to increase pressure. Gamma for the oil times 40 centimeters. And that brings me to the pressure at point 2, which is what I'm looking for. So this full expression is P2. So now to stick in my values, I need the specific weights. That's essentially all I have left in this equation to find P2. So specific weight of mercury, I can find to be 133,000 newtons per cubic meter. The table's in the back of the book. Similarly for air, 11.8 newtons per cubic meter. Then for oil, I know the specific gravity. So specific gravity I can relate to the specific weight of water. So for the oil, it's S times that of water. So 0.8 times 9,810 gives me 7,850 newtons per meter cubed. Now, interesting thing about this is when we deal with this, barometers, manometers, hydrostatic pressure in general, generally it's the liquids that we care about, not so much the gases, because gases are generally pretty light compared to liquids. You can see from here, air 11.8 compared to 133,000 or 7,000, almost 8,000 for the oil. So when we do this, if I wanted to just ignore this, I probably could, because it's going to be such a small contribution that's not going to change the answer, at least to the first few decimal places anyway. So if you have the situation, you can actually ignore this if you wanted to. I'm leaving it in there just to be completely complete. So putting those numbers in, P2, atmospheric pressure, 101.3 kilopascals, 101,300 pascals. That's assuming I'm going to answer in absolute pressure. If I want to answer in gauge pressure, to call that 0. Then mercury, specific weight, 133,000 newtons per cubic meter times 0.8 meters, minus this air, 11.8 times 1 meter, and then plus the oil, 7,850 times 0.4, gives me 211,000 pascals, or 211 kilopascals, again absolute using atmospheric pressure, or 110,000 pascals if I called atmospheric pressure 0. And again, notice if I did not use this, air, 11.8 times 1 is just 11.8, 12 essentially. I'd have 12 less in both of those. To 3 significant figures, even 4 significant figures, it's not going to change the answer. So even if I'd left that out, I'd end up with the exact same answer.